Hello, my name is Kartavya Soni, and today I am presenting a final project for computer vision. This project is a collaboration between myself, Jigar Purohit, and Vismay Gajera. So our project is titled as SOTA model comparisons for large networks. When we started this project, we noticed that most model comparisons focuses on massive server-grade performance using datasets like ImageNet. However, in the real world, developers often need to deploy models on limited hardware, like mobile phones, edge devices, or standard cloud instances, like without sacrificing too much on accuracy. Okay, yeah. To simulate a realistic, challenging scenario, we choose the Oxford-IIIT Pet Dataset. This isn't just a simple cat versus dog problem. It involves 37 specific breeds disguising a doll cat from a Burman cat or a Saffron bull from a pit bull. This requires the model to learn fine-grained features, not just general shapes. Our goal was to answer three specific questions. First is based on efficiency. Can a mobile optimized model compete with a standard VSNet? Second is modernity. Do a newer architecture like Convolution Next actually provide better feature extraction than older benchmarks? And third is the trade-offs. What is the exact cost in training time and memory to gain that extra accuracy? Okay. Yeah. Now about what I said. Okay. So before running the code, let's briefly explain why we choose this four specific model. So we wanted a representative from a different areas of deep learning. Design first, ResNet 34. This is our baseline. It revolutionized computer vision with residual skip connections, solving the vanishing gradient problem. If a new model can't beat ResNet, it's probably not worth using. Second is efficient net base zero. This model introduced compound scaling, optimizing depth, width, and resolution simultaneously. It's famous for doing more with less parameters. The third is MobileNet version 3 large. This is designed specifically for mobile CPUs. It uses hardware-aware network architecture search, which is known as NAS, and a special squeeze and acceleration blocks to keep operations low while maintaining accuracy. Finally, the heavyweight, the convolution next tiny. This is a very modern architecture. It essentially takes a standard CNN and modernizes it to look like a vision transformer. It uses larger kernels and fewer activation functions. We hypothesized this would be our strongest performer. Okay, so here I will show you the installation and usage. So I will clone this repository in my local system. So I already made a folder named start. So like this is a code for clone the repository. So I copy it, paste it. Now it will clone every data, like whatever files, whatever data, whatever code we have, it will paste it here from point one to point last. Okay. I think it's taking too much time to process. Still, we can do like create a virtual environment and activation it. So I have a Mac, so I will copy this to create a virtual environment. Oh yeah, it's done. So I will paste it, enter. You can see here like we are in virtual environment now. Okay, this is code for install dependencies. Okay. So copy, paste. This code will install all dependencies. So like I have already installed everything, so it will not it will not take much time to install everything. And We also have a like verifier, like here you can see at the bottom, we have a 139 dependencies in total, and it will check like from this to this everything. Okay, let's wait for this. Okay, yeah, it's ready. So first let me close this one. And now let's move to code. Okay, so here it is, the implementation. Okay, this is okay. Yeah, perfect. So first let me clear all outputs because it's cloned, so it will copy everything. Okay, we start the kernel. Okay, yeah, so now it's normal. So a crucial part of our setup is the team library. Instead of writing this architecture from scratch, which can lead to implementation errors, we load the official implementations using pre-trained is equal to true. This gives us a massive head start by transferring knowledge from ImageNet. Okay. And yeah, we didn't just wait. Yeah, here let me. I uh, I should mention this one. Yeah, yeah. So we didn't just write a simple loop. We built a robust enhanced trainer class to ensure the comparison was fair. Here you can see the implemented mixed spaces and training. This allows the GPU to use 16-bit floats where possible. It significantly reduces memory usage and speeding up training without losing accuracy. We also implemented early stopping. Let me get to the core. Early stopping. Yeah, here. Okay, so you can see the logic here. If the validation loss doesn't decrease, the patience is equal to 3 epochs, we stop training. This prevents the larger models like one next from overfitting it into the small dataset. Okay, so I am now starting the training pipeline. The script will iterate through all 4 models automatically. Okay. So since training 4 models for 10 epochs, it takes like 45 minutes to an hour on local machine. I will now don't take much time for this, and I already have a code, like I have already cloned another file here. So in which I can show you everything. Okay. So this is also clone one, but I haven't created a virtual environment. That's why it's showing these underlines. But it has all outputs, so I will show all detail and everything, like how it looks after training all model and everything. I will show it, showcasing it here. So in this one, I will not take much time. I will directly move to the results. Okay, so you can see like how 4 models architecture and all looks like. Okay, these are the code like parameter sizes and everything. Oh, what did this gaps for? Oh yeah, this is parameters and model throughout comparison and everything. Memory used and training function. This is for training. This is for printing the graph and where it is. Yeah, here you can see like here like model started training and it's like completed. So like for each model it take 10 epochs and train like 4 models. Okay, let's move directly to the result visualization. Yeah, here you can see like you can see like we have saved the base weights for each model into the save models directory automatically, so we can reload them later for interference and without retraining, like so it will reduce the retraining training time in total. Okay, yeah, here it is. Okay, so this is the most exciting part, the results. Let's look at the training time versus accuracy trade-off. So conversation next tiny. is a clear winner. You can see here. It has a massive 97.48% validation accuracy. It is basically near to the perfect. However, it was the slowest to train. Like you can see here, it took to 5,095 seconds in total for 10 epochs. Okay. And here you can see the mobile net is unbelievable. Like it got 94.49% accuracy, while it's near to the fastest you can see. Like you can see it took around 3,100 second to run, and the fastest one is 2,900. Oh my god. So mobile net is, I think, good one. Like it outperformed the wastenet and efficient net while taking very few time. Okay, wastenet took 2,900. It's the wastenet is the fastest one with accuracy of 93.19. Efficient net. Oh, efficient net took 4,497 second. Still, it has the lowest accuracy. Okay, that's not good compared to all other model. So for accuracy base, I can see like convolution next has the highest accuracy, and for the timing base with good accuracy is the mobile net, and with lowest timing, wastenet has a lowest timing. And every you can see like every model is trained on 10 epochs. No one has like emergency stop or something. And I have visualized this everything like total training time comparison, final validation accuracy, training accuracy, epochs completed. And I also have like plotting history of every model. So here you can see like this is the history of FastNet 34. In first graph, like here you can see like after epoch 3, it's almost like validation or training loss is very few. And same here, like after epoch 3, the training accuracy and validation accuracy is kind of not much differentiative. And for epoch time, you can see like after epoch 3, every epoch has kind of similar 300-second training time. And best validation accuracy for WasteNet is 93.19%. So I will not much take time to explain this in much detail because we have a limited time. Let me move to So this is for comparing the parameter and all four models after training. So here you can see like convolution next has the highest parameter 27.8 million. Afterwards, WasteNet follows it 21.3 million, and MobileNet and EfficientNet has kind of similar 4.1, 4.2 million parameters to compare. For model efficiencies like parameters per layer, how much parameters it take per layer. So for MobileNet and EfficientNet, like similar 0.031 parameter per layer, and for MobileNet 0.039. And convolution next has the highest 0.34 per layer. It's like 10 times to efficient net and mobile net. And WishNet also has a good parameters per layer, like 0.292. It's good. Okay, yeah. So layer count target versus actual. So here we have visualize the actual layer count versus a target layer count. So for WishNet we expected 34, like as WishNet 34, but we got 73. Like it's almost double. For efficient net we expected 24 and we got 131. Oh my god, I think 5 times. Yeah, 5 times more. For convolution next we expected 30, we got 82, near to the 3 time, in between 2 to 3 time. Yeah, for mobile net we have expected 35 but we got 110. That's, I think, more than 3 time. Yeah, something more than 3 time. Oh yeah. Okay, that's it. Like to wrap up this project, highlighted that I like you can see like it highlighted that architecture matters more than depth. Convolution Next, despite being a tiny version, outperformed the deeper Visnet 34 because of its superior internal design. However, there were some limitations in this all, like dataset size. With only 7,000 images, the larger models were at risk of overfitting. Through our early stopping, like it helped us preventing that. And we are lucky that we have early stop, otherwise model will be in like overfitting and it won't be good for finding a good accuracy. The second limitation is hardware, yeah, definitely. So we were limited to batch sizes of 32 or 64 due to GPU or VRAM with a server grade GPU. We could have tested the large variants of these models, definitely if we have better hardware. And the final question, what will we do if we have more time? Yeah, definitely, if we had more time, our next step would be model quantization for sure. We believe we could take the next conversion, next model, convert it to integer 8 precision, like INT 8 precision, and likely achieve the speed of mobile net while keeping that same high accuracy. Yeah, that we will do if we had more time. Yeah, that's all. So thank you for watching our demonstration. And the full code, logs, and pre-trained weights are available in the GitHub repository link. This concludes our presentation for computer vision. Thank you.